Okay, well now we're going to go ahead and take a look here at example number 1. Try to get a sense of how we can actually use this particular theorem to address certain kinds of questions. So let's see, example 1, determine with justification whether the series, listed here, converges or diverges. All right, so one of the things, again, that I typically want to go and make sure that I'm rehearsing for myself is that I actually have some types of series and some different tests to work with. So immediately I might try to ask the question like, boom, all right, is this the harmonic series? And when I go back and I look at it, no, that's certainly not the harmonic series. Is this a geometric series? Does it fit the form? Well, let's see, that would mean that my counter variable needs to be in the power. And no, that doesn't seem to be the case. Is it telescoping? Well, we know that telescoping series have something to do with subtracting of terms, so a lot of things can cancel out. And I don't see that initially. The only way I might be able to get there is by using partial fractions. And I don't see a way to factor that denominator, so I don't think that's going to be of use. We could also try something like test for divergence, which said, remember, take a limit of the stuff on the inside. And so oftentimes you'll see this as a really quick check that you can do mentally. In your mind, you'd essentially scribble this part out and just ask, if I did a limit as k went off to infinity, would that thing converge or diverge? Like, would I have a, well, sorry, not converge or diverge, but would it have a limit of 0? If it does, remember that means that test for divergence doesn't tell us anything. We needed to have not 0 in order to make a conclusion with test for divergence. So unfortunately here, all of the previous tests fail, but our new integral test can be very, very useful. I'm going to go ahead and just make sure that we do meet all of the conditions for the integral test, which said that when we convert to our matching function, it needs to be continuous, positive, and decreasing on the interval that we're working on. So here, it looks like since k is starting at 1 and going to infinity, I'm going to work with the interval 1 to infinity. If k was starting at 3, I'd use 3 to infinity, so on and so forth. Okay, so let's see. I'm going to start to say, let f of x be equal to 10 over 1 plus x squared. Perfect. And now comes a really, really easy part. I'll say, clearly, f of x is continuous on the interval 1 to infinity, right? I mean, there's nowhere where this function is going to become undefined or where it's going to have a hole or a gap or a jump. I can also say that this function is very clearly positive, right? The top's positive, the bottom's always positive, the whole thing's always positive. And I actually think it's really easy to state here that this function is decreasing. Because if I take a look at this, I can start to see something very, very important. Notice, as I continue to change the value of x, let's say that x is continually going to be plugged in as a larger and larger value, the numerator of this fraction never changes. And I can clearly see the denominator will only grow in size. Therefore, I can make the determination very quickly that this function must be decreasing. All of this is true on the interval 1 to infinity. Now I'm going to go ahead here and just add a quick little side note that you might want to go ahead and add for yourself, specifically dealing with this idea of a decreasing function. I can say here that we can just state decreasing if we have number over something that is getting larger. Okay, I'm going to always allow you to be able to do this. If you have a number over something that's getting larger, I think it's fairly obvious that we could just state decreasing based on our understanding of decreasing. But notice that means for things like x over x squared plus 1, I don't know if that's decreasing yet. And for something like this, I would ask that you go ahead and use your calculus 1 knowledge to prove that this function is actually decreasing on the interval 1 to infinity or whatever interval you're working with. This is very, very in line with the expectations from the most recent skills check. Okay, since I know though that this function meets all of the criteria, I know that I just need to look at the associated improper integral. So I'm going to say, let's calculate the integral from 1 to infinity of this guy. Again, I know that this is going to be a limit of an integral from 1 to t. I know that the antiderivative here is 10 inverse tan of x. And if I was to continue to evaluate, I see that I get 10 arctan of t minus 10 arctan of 1, but the inverse tangent of 1 is pi over 4. So this is going to be 10 times pi over 4. Now I'm interested in ultimately what the limit here is going to be. Again, if I think about my arctangent function, I'm curious where it's headed as t goes off to infinity. That would actually then be the value pi over 2. If you don't quite recall that, I would ask you to go back and take a look at the picture of the inverse tangent function. Now, I could simplify this down, but I really just need to note that this improper integral is convergent. Even I don't really need to know what it converges to, but now I can clearly write the following conclusion. Since the integral of our function is convergent, we know by the integral test that this series, oops, sorry, that should have a k in it, also converges. And we're done. Okay. So this is kind of an illustration of how we could actually use this theorem and the work that would be required to go into it. Again, the work might be slightly more involved based on this green note up here. If I didn't have a function that was number over something getting larger, I might have to actually do a lot more work to justify that decreasing part. But outside of that, this is the work that it would take every time. Okay. Let's take a look then at one other example here. Let's take a look at example number 2. What is the simplest way to determine whether the series, given here, converges or diverges? Notice that the emphasis here is on what is the simplest way. There are so many ways that we could tackle this, but I'm not interested in all the ways. Typically, I want to try to find the way that's short as possible. So like if I think here about the integral test, I might be able to quickly determine that on 1 to infinity, this is a continuous function. Or the matching function here would be continuous. I'm definitely only going to get positive stuff out of here. And the idea though of decreasing maybe seems difficult to justify. I definitely don't have just a number over something getting larger. And I would really be careful with what your intuition leads you towards when analyzing a matching function for a series like this, because you may actually tend to guess wrong more often than you think. But here, I might note that I don't even need that approach. Take a moment here really quickly. Can you think of an easy way to determine whether that series converges or diverges? If you need to, pause the video for a second to think about it. Okay, here's the way that I think is easiest. I'm going to go ahead and think about the matching function that I actually have here. So I have f of x is going to be equal to x plus 2 over x plus 1. Then I'll say that clearly the limit of f of x as x approaches infinity by L'Hopital's rule should be able to be simplified to a limit where x is approaching infinity of 1 over 1, which is 1. But if the limit of the matching function is 1, then that means that the limit of the inside formula, which I'll just write as k plus 2 over k plus 1, this thing must also equal 1. Last time I checked, 1 is not the same as 0. And by the test for divergence, the series diverges. Test for divergence is freaking awesome. That should be one of your #1 approaches almost every time you take a look at a question. Because again, you can really easily just cover up the series, quickly do a mental check of that limit, if it's easy enough. Most of the time it's fairly simple. And then immediately you might know the answer and can just write out everything nice and formal. Okay? So in this case, there was no need to go to an integral test, although you actually could. This matching function f of x surprisingly is decreasing on the interval from 1 to forever. In my notes online, I do actually show how that could be done. Okay? And if you're interested, you can go ahead and take a look at it there. It's important to keep in mind that when we get to questions in the worksheets, which again, I'm going to highly suggest that during this time you practice worksheet questions, that you keep in mind that there are multiple ways of tackling a question. If I did this by the integral test and my solutions showed that I did it by the using the test for divergence, it's not that one answer is wrong, it's just that some answers are shorter than others. If you're ever feeling maybe a little unsure as if the approach that you took is valid, especially maybe after seeing my solutions and seeing that something that I did is vastly different than what you did, by all means, please let me know and I'd love to take a look at your work. You can always send me a picture, okay? All right, well that concludes at least this portion, or concludes this entire lesson, and we'll pick up next time with 5.3.3.